Okay. A 15 kilogram object and a 12.5 kilogram object are suspended, joined by a cord that passes over a pulley with a radius of 10 centimeters and a mass of 3 kilograms. The cord has a negligible mass, it doesn't slip, there's no friction. They start from rest 3 meters apart. Treating a pulley as a uniform disc, determine the speeds of the two objects as they pass each other. So, here's the little picture. Just because we're using energy and we're going to need like a point of reference, we're going to call right here like 0, meaning that this mass is at 0 meters, and then this would be at 3 meters. But we'll get to why that's important. So first things first, it wants us to determine the speeds. That's a trick question. They're on the same string. The string can only go one speed no matter where it is. So we're just looking for the speed of like this, I guess the speed of this rotation of when they meet each other, and they would meet each other at 1.5 meters, which is like halfway between right here, because it, like I said, it's about one string. So this is where the string would be even. So conceptually, that was a little tricky for me to get, but okay. So since nothing's getting lost to friction or anything, nothing like rotating or anything or slipping or anything, we're just going to say initial is final for kinetic energies. That shouldn't be kinetic, that should just be potential. But anyways, setting up this equation, going from this step to this step was the real doozy, and why I struggled so much with this question. I just figured there had to be more on this side if I was going to have 5 terms on this side. So that's why I struggled so much, and that's where I wanted to do this problem. But let's go through it. So remember, mass 1 is the one that's kind of being suspended initially, and mass 2 is the one that's on the ground initially. We have the gravitational potential of the first one, like the suspended one, initially is its speed, the other mass's speed, the rotational kinetic of the actual pulley, and then the mass's final positions. So plugging that in, moving that like onto the next step, the easy stuff, just mgh, and then any k is half of mv squared, and then this k3 is going to be half of I omega squared, because it's the rotational kinetic energy of this thing. And then again, it's just mgh, whatever. Plugging stuff in. Since this is a uniform disk, we can use mr squared. And then I used v over r, because omega is v over r. And then you just plug that in squared. I'll write that down. Ready? Boop, boop, omega. Like that. I just use that equation to do this. And then just plugging all this stuff in. A really important thing, like I said earlier, since these are going to be crossing at 1.5 meters, you have to use their final gravitational potential. The h here is going to be 1.5, because they're meeting at that 1.5, which was just, it's part of the conceptual problem, part of like the conceptual difficulty I have with this problem, and why I think it was so challenging, and why I think like you chose it to make a video about. And then you just, you solve for v, it's 1.59 meters per second. It's a pretty easy problem. I would just say, just setting this up like